So building on the last video, the pH scale is simply just a convenient way to express or represent the concentration of H3O+. With an equation of pH is equal to the negative log of that H3O+. So why do we use negative log? Well, when we take log terms, we get rid of that scientific notation, and now we have whole numbers. And so we have a scale from 0 to 14 rather than a scale that's exponential from 10 to the minus 1 to 10 to the minus 14. And we use the negative here because it takes that negative exponent and makes it positive. So our pH scale is positive numbers, though our scientific notation of H3O plus is always represented as 10 to the negative something because it's always less than 1. Okay, a quick example is just what's the pH of a solution where the hydronium ion concentration is 10 to the minus 2? Well, it's literally just the negative log of that value, and so we can look at this and say the negative log, the log of this thing is going to be negative 2. Negative of that means that the pH here is simply going to be 2. You can convince yourself of that by writing it out on a calculator. And similarly, we can look at the pH of a solution that's much smaller, so 10 to the minus 12, no different. Negative log of 10 to the minus 12 is just 12. And so if we think back to the previous video, I mentioned that you have acidic solutions. Acidic is a condition where the concentration of the hydronium ion is going to be greater than the hydroxide ion concentration, which implicitly is 10 to the minus 7. So really that's anytime it's greater than 10 to the minus 7. And in this case we have 10 to the minus 2, or a pH of 2. So we would consider this to be an acid, and by the same definition we would consider this to be a base. And this definition of anytime hydronium ion concentration exceeds 10 to the minus 7, we could also just say anytime the pH is less than 7, that's acidic. If pH is greater than 7, it's basic. And so these rules are the same. Essentially, you're just negative logging the rule, and you're getting the pH scale. So P in chemistry is always just negative log. So negative log is implied when we have P. In this class we only talk about pH, but in other classes we can talk about P of anything that's a concentration. So if we're thinking about calcium ions, we could say P calcium or P sodium, etc. So P just represents negative log of whatever that thing is as a concentration. So by that logic, POH could also be written here. That's simply just the negative log of the hydroxide concentration. And since we know this to be true, the equilibrium expression for the odds association of water, that has to be true always with water, then we could simply take the negative log of all of these things, right, and have our relationship between pH and POH. So if we just negative logged everything in this expression, what we'd end up with is 14, because negative log of 10 to the minus 14 is 14, is equal to, and was the negative log of H3O plus? Well, we just said that was pH, and the negative log of OH, OH is POH. And so pH plus POH has to equal 14. And so that's the origin of the pH scale being from 0 to 14. So a quick but important side note is thinking about sig figs when we're thinking about log transformations in pH, because we're going to be doing a lot of this in the class, and we haven't explicitly talked about sig figs and logs and exponents. So an example might be that you're trying to compute the pH of a solution where the hydronium ion concentration is 2.5 times 10 to the minus 3. So you would simply take negative log of that, and that would give you some value. But how many digits do you preserve in this pH value, because you're doing a mathematical operation? This isn't addition, subtraction, multiplication, or division like you did before. A slightly different way to think about this. So if we were to pop this into the calculator, negative log at 2.5 times 10 to the minus 3, we'd end up with 2.6000. When we're thinking about sig figs in these logged terms, Notice that the number that's being input into the equation has 2 sig figs to start with. And so we're constrained by that. We can't have any more than 2 sig figs in the answer that we compute. But what's important to know that when you're doing a log transformation, you're essentially converting this number, which is a placeholder for the number of zeros, right? 2.5 times 10 to the minus 3 is the same as 0.0025. So you're capturing this here, and when you log that, that's what's captured in that 2 in the front. It's telling you, oh, I've got 2 zeros in front of the digits that I'm log transforming. And so that's a placeholder. Those aren't real numbers, so there's no actual significance to them, just as there is no significance when we write it 10 to the minus 3. We didn't consider these as significant, we only considered these two. So the pH then would be written out as 2.60, where only the last 2 digits are 2 sig figs. So the rule here for log transforms is that you should have the same number of sig figs going in as going out, but that first digit is not significant. It's only representing the zeros, and so you apply those sig figs only to after the decimal place. We call this, you may have heard of this before, we call this the mantissa of the log term. Everything beyond the placeholder number. The first number is placeholding of the zeros, and that second number past the decimal, that's the mantissa. That's where we conserve our sig figs. And that feels a little counterintuitive because this number itself has 3 digits, but we would consider only 2 of those digits to be significant, only real interesting numbers, because that one again is considered a placeholder. So see if you can apply the same logic to this problem. Pause the video and see if you can work out a number, punch this into your calculator, and figure out how many digits are significant. How would you write that pH value? So start by identifying number of sig figs in the input value. There's 5 of those, so punch that into your calculator. You probably get a number that looks like this. And remember, I have 5 sig figs here. That means I need 5 past the decimal, because the 5 here is just place holding those zeros. And so I would have a number of 5.71343.